Hey guys, welcome back to part 2 of our discussion about ionic bonds. Today we're going to talk about some really important things that are key to understanding what's going on. So first off, I'm going to show you the crisscross trick on how to form ionic compounds. It's a trick we use instead of having to do Lewis structures. You get the same answer both ways, but this is a really fast trick. Then I'm going to show you how all ionic compounds form neutral charges, overall charges of 0. And then we're going to determine how to figure out the charges of transition metals. We've been ignoring transition metals, but now we're going to get into them a little bit. And then finally, we're going to talk about naming ionic compounds. Okay, so the first thing we'll talk about is how to do the crisscross trick to form ionic compounds. It's a really fast way to see what our ratios are going to be of metals to nonmetals without having to do Lewis structures. So here's what we do. We take a metal. Let's take magnesium. We're going to put our charge up here. We know magnesiums are all +2. And let's take, I don't know, phosphorus. Phosphorus, -3 charge on those. So we're going to take advantage of the charges to do this trick. So here's how it works. Now that we know the charges, just write the elements side by side without the charges. So now we're going to take the numbers here, just the number, this number 2, from the magnesium, we're going to crisscross it over to the outside of the phosphorus. We're going to put a little 2 right there. And then we're going to go up to the phosphorus. We're going to take the 3. We're going to take it and we're going to move it down here. We're going to crisscross it over outside the magnesium. There we go. So now we have Mg3P2. So that's the crisscross trick. Don't worry about the plus and the minus up here. That has nothing to do with what we're doing. This is just a trick using the charges of our metal and our nonmetal. All right, let's try another one. What if we have some sodium, that's a +1, and then an oxygen of -2? All right, so we'll write them next to each other. There's the sodium, there's the oxygen. Now let's crisscross. The 2 from the oxygen, we're going to cross it all the ways over down here and put it on the outside of the sodium. And then the 1 that's by the sodium, we're going to crisscross it down here outside the oxygen, but we don't write 1s. If there's no number there, that's implied that it's 1. So we're done. This is our formula unit for when sodium and oxygen bind together, Na2O. All right, let's look at another one. How about if we have some calcium +2 and maybe, I don't know, let's try a fluorine -1. All right, so then let's write our elements next to each other. Leave a little room in case we need to put some numbers in there. So the calcium, the 2 from the calcium will crisscross to the outside of the fluorine. And then the 1 here, that's from the fluorine, we crisscross it here after the calcium. But again, we don't write 1s. So there we go. There is our formula unit for when calcium binds with fluorine. Again, this is only showing you the ratios. We have 1 calcium that will bind with every 2 fluorines. This is what it means. We're talking about ratios. Here we have 2 sodiums will bind with every 1 oxygen. Here we have 3 magnesiums will bind with every 2 phosphoruses. You would get the same answers as if you did a Lewis dot structure, but this is just a much easier and quicker way to do it. Okay, so let's try another one here. Let's say we have some magnesium with a +2 and then a sulfur, which is a -2. So let's see what happens here. Because they're both 2s, obviously if you crisscross them, we're just going to get 2 and 2. But remember, we need to reduce these down to their lowest whole number ratios. That's what a formula unit is. So whenever these are the same, or you can reduce them down, if say it's 2 and 4 or 3 and 3, whatever it is, you reduce it if you can, and this is going to simplify to MgS. This is the proper answer, because for every 1 magnesium, we have 1 sulfur. Same as a 2-to-2 ratio. 1-to-1 is the same as 2-to-2. Here's another one. What if we have titanium with a +4 and then some oxygen that's a -2? All right, let's crisscross these. Here's our titanium. Here's our oxygen. The 4 from the titanium is going to crisscross over to here. The 2 from the oxygen is going to crisscross after the titanium. All right, so here's a chance where we can reduce it. We have 2 and 4. If we divided these each by 2 to simplify, we're going to get TiO2. That's our formula unit. And this is how titanium and oxygen would bind. For every 1 titanium, there's 2 oxygen. So remember to reduce. Okay, so let me prove to you that all ionic compounds have an overall charge of 0. This is what they all do, and it's one of the reasons when they form compounds, they have an overall charge of 0. So let's say we have some sodium, we have some chlorine. Okay, sodium chloride. So what's happening here? Let's look at the charges. Sodium has a charge of a +1. Chlorine has a charge of a -1. We have to remember that overall ionic compounds have a net charge of 0. So we have a +1 plus a -1 that equals 0. This happens for all ionic compounds. Okay, so let's look at another one. Let's say we have some magnesium and some fluorine. There we go. That's the formula unit for when magnesium and fluorine come together. So let me show you why these end up having an overall charge of 0. So let's take the fluorines. We have 2 of them. And we know that fluorines carry a charge of -1. So then we have 1 magnesium. So if overall the charges are going to be 0, imagine all this is in like one giant beaker. We have -1 plus -1. Our nonmetals overall have a charge of -2. So for all this to add up to 0, what does the charge have to be on that magnesium? That's right, it has to be a +2. And we know that already because magnesium is in group 2, so they're all +2. How about some transition metals? Let's look at iron chloride. All right, so we have to figure out the charge on that iron. It can vary. Transition metals can have a bunch of different charges. Iron could do a +2, it could do a +3. So let's see which one this is. So again, let's take a look at the ions individually. We have 2 chlorines. They're each -1. We only have 1 iron. Again, if we have these all in a beaker, -1 plus -1 is -2. So the iron has to be a +2. See how this all adds up to 0? 0. So this iron is a iron 2 ion. It's important to be able to figure out the charges of transition metals. Knowing the charges and understanding about ions is really, really important as we move forward. So let's do another one here, maybe one that's a little trickier. How about we're trying to find the charge of this titanium compound. We have 2 oxygens. We know oxygens have a charge of -2. Because all oxygens do, it's in group 16. Everything in group 16 has a charge of -2. So we only have 1 titanium. So what does the charge of this titanium have to be if our nonmetals add up to a -4? This has to be a +4. There you go. +4, -2, -2, that all adds up to 0. How about another one? Let's figure out zirconium and nitrogen. What happens when these 2 guys come together? What is the charge on the zirconium? Well, let's do it this way. We have 2 nitrogens. We know nitrogens carry a charge of -3. because they're in group 15. All elements of group 15 have a -3. So this time we have 3 zirconiums. So if we have these guys here that add up to -6, this entire side has to add up to +6. So what's going to be the charge on each of these zirconiums here? Nice, +2. These are all going to be +2. +2, +2, +2. This adds up to 6. -3, -3. This adds up to -6. When we add these together, we get 0. Okay, and then finally for today, we'll just talk about how we name ionic compounds. And they're not very difficult, especially now that we know how to get the charge on transition metals. So let's take a look at this. Okay, so here's one that we're all familiar with, NaCl. So here's the rule. First off, your metal, all you do is say the metal name, sodium. Nothing too difficult about that. Here's the tricky part, and although it's not tricky, our nonmetals are always going to end with the suffix IDE. You kind of chop off half of the word chlorine, and we call it chloride. IDE, sodium chloride. Very simple. Metal, regular name. Non-metal ends in IDE. Always, always, always non-metals end in IDE. All right. How about this one? Let's look at MgO. Our metal is magnesium. And oxygen becomes oxide. You've probably heard the word oxide before. All right, let's try a couple more. How about lithium? And let's do sulfur. All right, so notice the 2 here, because this is the ratio that they form. We don't have to worry about the 2, though, when we're naming ionic compounds. So we just call this lithium, and sulfur becomes sulfide. Easy peasy. And let's look at one more. How about calcium and nitrogen? That would be the formula unit for this. And I did this quickly because I did the crisscross trick in my head. Calciums are +2, cross over there. Nitrogens are -3, cross over there. It works with every single ionic compound, metals and nonmetals. This is what they all do. All right, so our metal is the calcium, so we just write calcium, and then nitrogen becomes nitride. IDE. IDE. All nonmetals end in IDE. All right, so let's look at transition metals. How about this compound here? Fe2O3. So let's name this iron oxide. Okay, but wait a minute. What about this one that we did before? Remember, this iron was a +3. We figured out this iron here was a +2, but these are 2 different compounds. This one, can this one also be called iron oxide? I think not. Otherwise, how are people going to know which one you're talking about? So here's the trick to this. Transition metals need Roman numerals in between the words designating the charge on what the metal is. So in this case, it was a 3. So this is called iron 3 oxide. Over here, this iron was a +2. So we're going to put the parentheses here. I should have left some more room. Iron 2 oxide. We're using Roman numerals to tell people the charges of our transition metals. So for naming ionic compounds, you always write the metal, and then the non-metal with the IDE at the end. But with the transition metals, you have to add in the charges using Roman numerals. All right, let's look at a couple more examples here of transition metals. Let's do this copper and oxygen combination, and let's do this copper and oxygen combination. Both copper and oxygen, but what's the charge on this one? What's the charge on this one? They're going to be different, so we have to tell people the difference. They're both going to start off as copper oxide. Copper oxide. What's the charge on this copper though? Since there's only one oxygen and oxygens have -2 charges, what does that copper have to be? It has to be a +2. That's it. There's 1 and 1. If that's -2, that has to be +2. So we're going to put a Roman numeral 2. All right. How about this one over here? There's two oxygens, and they're each -2, so that's a total of -4. So what does this copper have to be since there's only one of them? +4. Nice. So we're going to call this copper 4, IV is 4, copper 4 oxide. So we have copper 2 oxide, we have copper 4 oxide. Two totally different compounds. So to be able to do this, you have to know your Roman numerals. So you're going to be required to know 1 through 10. 8, 9, 10. Okay, so here we go. 1, Roman numeral 1 is just an I. 2 is 2 I's. 3 is 3. 5 is V. So 4 is 1 before 5, which is IV. All right. 6 is going to be VI, 5 and 1. Let's just put these here so we can separate them a little bit. 7 would be 5, 6, 7. 8 is 5, 6, 7, 8. 10 is X. So what's 1 before X? It's, of course, 9. All right, let's do some quick examples of, say, 4 different compounds. And I'm going to mix up transition and representative just to show you how the naming goes, because you have to distinguish between all of them. 2 of these are representative, 2 of them are transition. So in every case, doesn't matter what, you're going to start off like this: lithium bromide, iron chloride, copper sulfide, and magnesium oxide. Okay, so notice the metals, we just said the metals of each of them, not too tricky, and then the non-metals end in IDE. All right, that's the same no matter what. But now we have to come here and look to figure out if there are transition metals involved, because then we need the Roman numerals. Is lithium a transition metal? No. Okay, we're done. Lithium bromide, that's what that is. Is iron a transition metal? Yes, it is. So right away we know we need Roman numerals. Put the parentheses in between iron and chloride. What's the charge on this iron? Have to figure it out. You can kind of do these in your head when you get better at it. So if we have 3 chlorines, chlorines are -1. So overall, this is -3. So your iron has to be +3. This is iron 3 chloride. Copper. Is copper a transition metal? Of course it is. So we need the Roman numerals. We need to tell people which copper we're talking about. So if sulfur is -2, we always know the nonmetals, -2. But now we have 2 coppers that have to add up to cancel out the -2. So it's going to be 1. The charge would be +1. Copper 1 sulfide. Magnesium, oxygen. Is magnesium a transition metal? No, it's not, so we leave it alone. Magnesium oxide, no need for Roman numerals. All right, so again, we need Roman numerals to tell people the charges of our metals. Representative metals are always the charges that they are. They don't change. So there's no reason to tell people that lithium is 1, lithium 1 bromide. It's always 1. We don't need to tell people magnesium's 2. It's always 2. We only have to do it for the transition metals because they're always changing. All right, that's it for today. So we only have one more thing to do in this unit about ionic compounds, and that will be part 3.